everyone. Hello. This is episode number 10 of the Amiga assembly course. I need to say thanks also to Fabio Ciucci for letting me stream his book, his Italian book, and also say it in English. Okay, so let's start with where we are. And as you know, we are here actually. We going to start chapter 4, and this chapter starts talking about how to have screens, or how to display screens on the Amiga. Okay, so far we are able to display some type of color to the screen, but we haven't been able to display any images. So yeah, so far in the previous chapter, chapter 3, we only used the copper and we changed colors on the screen, but there was no real, using the copper bars and stuff like that. But we never saw anything in terms of an image. So today we should be able to start seeing that. And we actually only used colored 0, okay? To display an image, we need to tell the Amiga that we want to display an image using BPL con 0 or DFF 100. So I'm just showing my notes here, okay, what the paragraph is showing, so that you can like that. So you should be able to follow what I'm saying in English, because I wrote my notes in English. Of course, there's typos, but who cares, for me they are just notes. So far we have always kept the register value of BPL con, so DFF 100. This register, we always kept it at the value of 200. Okay, that means that we had no bit planes. Okay, just blank screen. Basically, that's what we did. After, we need to set, so once we have something on the display, we need to actually tell the Amiga that we need bit planes. So we need to set the bit plane pointer so that the Amiga knows where the image is. Okay, so this is how. So when we tell BPL con 0 with our value, that we want to display an image, we need also to set the bit plane pointers where the image is, and the image is composed of bit planes, which I will explain in a minute. We also need to define the colors. So after we define the bit planes, we need to define the colors of the image. So if we have a 2-bit plane image, okay, that means we have for colors, 1 bit plane can only have 2 colors. Okay, no matter how many bit planes we have, a 1 bit plane can only display 2 colors. But in combination of all of them, superimposed one on top of the other, then you get what colors you need, and I will be showing that. So as a summary, we set the resolution and the number of bit planes in DFF 100. We need to define the colors from for the image. Okay, those are basically the steps. It's very high level what I said here. We will go into more detail. Okay, so before we can define an image, we need to have an image. Okay, so the author Fabio tells us that we need to use KEFCON or Keference image converter or Keference converter, or whatever you want to call it, or IFF converter. That's what it is. It's Keference IFF converter, which basically what it does is, IFF images are not something that the Amiga can recognize. Okay, we load them, but in assembly they are not recognized. you need a routine to display an IFF image. The Amiga hardware is only able to display images that are raw images. Okay, so we need a tool to display somehow something that is IFF to convert it into raw. Okay, so this is why you need to know how to use the Kefren's IFF converter. There is another tool also which I find better than Kefren's, which I will go through it. But for now, I'm going to cover Kefren's IFF converter because this is what the book talks about. So, and I will be going in short. Yesterday, I think I went a bit too much in depth about it, but I shouldn't. To be fair, especially after you see my tool, the tool that I'm going to recommend, because of course when the book was written, this tool was not available. So, first of all, because I have a high resolution screen and Kefren's doesn't work with a high resolution screen like what I have, I need to lower my resolution and I need to make it I think, yeah, 640 by 256 is fine. So use, and we go to 640 by 256. Then we load Kefren's GFX tools, and here I have Kefren's converter, and there you go. That's Kefren's IFF converter. Okay, it's on the discs, okay, of the book. Okay, so because the book talks about this one, I need to cover this one. So one of the limitations of Kefren's IFF converter is that it can only read from hard disk DH0. Okay, so you select CD DH0, click read, it reads the directory. Then I have a workspace directory. I go there and then I go in images. And then I'm going to load one of the images, one of the, I don't want to load one that I loaded yesterday, so that I color merge. Let's load that and load it. Ooh, it made a mess. Okay, so I don't want to load one of Malta. Magnifying, let's do this. Load. Oh my god, it doesn't want to load. There you go. This is from some game, I assume. But anyway, we have an image. Okay, it's not important. The important is that you understand how you convert from IFF to RAW. Okay, so, and this one is a 3-bit plane image. Okay, so width is 320, height is 256. Okay, and we need to save it as raw. Okay, so what you do is select raw. Okay, and then you have options. Okay, on the right, you can either save the image without color, or you can save the image with color. Okay, so we're going to save it without color the first time. Okay, so dot raw, and there you go. We saved it without color. Then we change this to either before the image, before the bit planes, there is the image, the color, or we use the color behind. I prefer color behind, so I going to select behind. So first there is the image, and then there is the color information, and I'm going to save it again, and I'm going to call it row 1. So one was raw and the other one was raw one, so I know which one is the what is the difference. Okay, so save, and that is it. Basically, that's what an what reference IF converter does. You can also select images if you want. I can select, for example, this image, and it will just save what I've selected. Okay, and it tells you what you've selected up here. Okay, and then it will select. Also notice that when you select, it also displays you see those in columns, let's put it this way, these lines that you get, that each one of them is 16 pixels, which is for sprites also. So if you have a sprite, you know that you are in the right border, let's put it this way, or in the right column. But that's basically it. Not much. Please note that reference IFF converter uses the hardware directly, so that's why I need to lower my resolution, because it would go messy. Basically, it doesn't understand, of course, graphic cards as I have in my emulator. Okay, so now I'm going to show you the other tool, okay, that I was talking about. So if I go into progs, my progs and my tools and GFX tools, most of these are converters, okay, some to ANSI, some to IFF. So this is what tools I use. I have so many, but the best one yesterday I was showing AGA IFF, but I'm going to use AGA IFF too, which I'm going to share the link to it too. There's documentation. The documentation is quite good actually. As you can see, I'm going to show it to you for a minute. Okay, it's quite good. It goes in detail. So this is the yesterday it was showing me beta actually, but today, as you can see, it's not showing beta. I hope you can see the screen because I know it's small, but I hope it's readable. Okay, so first thing is to load an image, but before you load an image, you need to tell it which resolution you want to do. So we're going to do low res, okay, 320 by 256, and we're going to tell it to load an image. Now you can select any volume, not like reference. You see, I have all these volumes. Well, these are the main volumes, but these are assigns. But I'm just going to go to the same directory, workspaces, images, okay, and I'm going to do another one. Let's load effects, whatever that is, and there you go. We have an image, okay, and it's showing us the image, and we can do selection also and stuff like that, okay, like what we had before in the IFF converter. What I'm going to do, I'm going to right mouse button, you exit from when you load it. So I'm going to load it again, just to make sure that let's select another image, or actually let's select Earth. There you go. This is a nicer picture, I think. So right mouse button, and we will convert that from IFF to RAW. Okay, so it's very easy. It has lots of options, but if you notice, we loaded an IFF to or ILBM image. Okay, so that's the option, but you can select various options, as you can see here. Okay, I going to use it's also support for PC, to be honest, but yeah, raw standard. Okay, and you can also save in for assembler as data files, or for PC, okay, but I'm going to use a file, so raw. Okay, I'm going to leave it no colors as we did with the FF converter, and of course we didn't load you know, an AGA image, so by default the Amiga is 12-bit. Colors 4096 is 12-bit. Okay, and then we're going to save it. So, and we go to the same directory where I was. Go to the same directory now. Workspace, images, and we selected the earth pick now. So now I'm going to say that this one is 320 by I think it was by 256. I can't remember. Anyway, it doesn't make a difference. And it is 16 colors. So 3-bit planes. And this is raw 0 or raw. Anyway, and we save it. Now I'm going to save it with colors again. Okay, and I'm going to save it so the colors at the bottom. And we save it, giving it raw 1 now, so it will be like the other one. Now, what you need to understand, let me open the directory. Okay, so I'm going to show you in DOS, okay, what happened, because this directory is shared between the PC and the Amiga. So it's easy for me to show things. Let's give me a second, because I do not want to show. Okay, so now we need to go to my drive. That was not right the way I did it, not intelligent. I closed one drive because the drive is on one drive, and then I needed to open it, so doesn't look right opening it and closing it. Okay, there you go. So this is my hard drive and workspace. So what I want to show, let's find Earth under images. Okay, this is what I saved with the AGA IFF. So without the images, remember it was 3-bit planes. I think it was more actually. I'm seeing the size. It's 153, but that was a lot more. That is, oh god, that is quite. I'm going to load it to make sure. I thought I loaded a 16 color version. So, it was hem. Jesus Christ, no wonder. No, but here is Earth normal. That's quite high though. That's quite high. So it is, oh, it's 640 by 480. Oh, okay. And 16 colors, of course. But okay, let's not do 640 by 480. That's why it jumped to higher res there. Let's do another one. Sorry, so I will confuse you. Let's do, I don't want to do hostages. Since we did it with the friends, and I will show you. Let's do Venus, whatever that is. Yeah, this one. Okay, so that is, it's 5-bit planes. Okay, it's saying here 5/8. Okay, and the resolution is 320 by 200. Okay, so I'm going to save this again. and this time no colors. Okay, and save, and it is row 0. And I'm going to save it again with colors at the bottom, and we call it row 2. Okay, I left the, why I left the file name the same? Oh Jesus. Today I'm making one mistake after the other. This is underscore 320 times 200 times 5. It is. Okay. Dot row 2, because this is with color. Row 1. And let's save it. I'm going to save it again with without color, because I want to show what is the difference. So let's bring my folder again on DOS, and Venus, we have it. Okay, so 320 by 200 times 5. So that is a size of 40K. Okay, it's this size. Okay, so if we do 320, okay, those are pixels. We need to convert them into bytes, division by 8, okay, times, which is 40, times 200. 1 bit plane is 800, okay? So, and then if we do times 5, that will bring it to 40K. So I'm going to explain better, okay, what bit planes are and how they are. But for now, just bear with me for a second, because he started explaining the tools. So that is for 40K or 40K of image, okay, without color. Now, the difference between an image without color and an image with color is this. You can see there is 64 bytes, okay, difference. So it's 4K plus 64. However, each color, okay, so because it's 5-bit planes, it is 32 colors. So you expect 32, but actually each color is 2 bytes. Okay, so it should be 64. So because 32 times 2 is 64. So that is the difference. So sometimes you will get, you might not save things properly, and you need to know how you saved your image, and if these numbers are correct, and you will need to check the file length, etc. And this is how you know. I do not, so guys, I do not have any, at least I haven't seen any moderators today. So if I do not see your messages, please just type it again or something like that, because I'm noticing that you have typed some things and I think I missed them. Okay. So that is the difference between an image with color and without color. And I also showed the reference, IFF converter, and the AGA IFF, which I think it's a better tool. We have our image as raw. Sorry for what? Can you repeat it? I said, did you wrote your program? Did you write it in C or in assembly? I assume you wrote it in C. Yeah, of course. Such a tool is better to write it in C than in assembly. This is where I agree on using C and not using assembly on such things. Anyway, Yeah, of course, it's command line. I mean, you don't need um, graphics GUI to do that, but you can add GUI, you know. Anyway, let's continue with our book, because now I will be skipping from the book now because it talks a lot about the IFF converter, which we covered. So why is not, oh, it's here. It's appearing in the wrong window. So that's how KEFCON works, or IFF, IGIFF works. Please note that although I gave an overview of how to display an image, or what you need to do to display an image on the Amiga, there are other registers which he is going to mention, like in Italian is moduli, modulo, no? It's modulos or modulo in English, and you can select interlace or overscan, as he says it. He uses the word overscan here, and other stuff. We will discuss all those. So, in short, there are other registers to regulate a screen on the Amiga, such as modulo start and stop of screen and data fetch. Okay, please note that there is a huge difference between an image created and saved by dpaint in IFF format and that used by Copper, which is bitmap or raw. Okay, raw data. So I mean bitmap is raw data. Okay, so on the disk there is a program, yeah, which we covered, and he is explaining how to use KEFCON, but I'm going to cover bit planes now. And yesterday I had an error which I fixed. This color 0 was was 111 instead of 000. Anyway, we have 3-bit planes, okay, blue, red, and black. Okay, bit plane 1, bit plane 2, bit plane 3. Imagine these 320 by 256 lines. Okay, so 1-bit plane is 2 colors, 2-bit planes together is 4 colors, 3-bit planes together is 8 colors. Okay, so that's the first thing that you need to know. So it's the superimposition of each bit plane on top of each other. Now, if we take so this value, okay, so here is we have 111. So 111 in binary is 7. I haven't done 7 here, but that means it is color number 7. However, the next one, okay, is 100. So 100 is color number 4. So we know that color number 4 is blue. Okay, it's OOF. Remember, this is red, green, blue. Okay, and this is how it works. So we did this one. Now let's do the third one. So it's O. Remember, you have to start from a bit plane 0. So this is our bit plane, and bit plane is the size of the screen. Okay, so 320 by 256. So it's 010. So 010, that is color number 2, and color number 2 is red. Remember, there's a 0 here in the front, but so 0, red, green, blue. Okay, and we continue like this. This is how an image gets the color, by having bit planes superimposed on each other, and then according to the bit patterns that they have, okay, they combine a color. A bit plane, as I said, can only have, as you can see, 1 or 0. It's only when they are combined together, that means 2 colors. It's only when they are combined together that you manage to get more colors. So 5-bit planes is 32. 4-bit planes is 16. 8-bit planes is 8. Sorry, 3-bit planes is 8 colors. 2-bit planes is 4 colors, and of course 1-bit plane is 2 colors. So that's how it basically works. The system of bit planes on the Amiga. Here he's showing, okay, he's showing that 1-bit plane. Okay, here you have an image of a person, uomo. Okay, person. Here you have an image of the letter A, and here you have an image of a plane, but it's always 0 Z1, which is 1-bit plane. Okay. Since figures can be large and have multiple colors, it is difficult for us to do these by hand on a piece of paper like what he did here. Okay, so we use programs like dpaint or personal paint to draw our images. Of course, in today's world we use the PC, and then we convert, but we use these type of tools to create an image. Okay, when we have a 2-color image, we use color 0 to define the background image, which is DFF. Remember, it's registered DFF 180, and color 1 to define the color index, basically 1. Okay, which is whatever color we have on the screen. So this paragraph is saying, let's talk about the IFF converter and what it does. I already explained that. And then he's showing more. I explained everything about the IFF converter. He's showing more about it. And he's showing the different, the resolution and what happens when you use the IFF converter. Now, note, and this is important, there are only 2 resolutions in the Amiga, okay? That is low res 320 by 256 or 640 by 256. But then there are enhancements to these, okay? So, but the basic resolution is this, and most games are either 320 by 200 or 320 by 256. The reason why is in high res 640 by 256, you can only have 16 colors maximum. Okay, so that is the generic rule. I mean, this is standard Amigas without having, I'm not referring to AGA now, we're talking about OCS, and we also talking no graphic cards, etc. He is saying here that the image in theory can be as long, not as 256, but as 312. Okay, there are 312 lines actually on the display, but not all monitors are able to display 312 lines also. But if you want, you can have an image which is 312 lines long. Now, he's going to talk about the other modes. There are, note, low res can have up to 32 colors, as I explained. So 320 by 256 can have 32 colors. But there are 2 extra modes. One is called half bright, which permits you to use to have 64 colors in a tricky way, okay? And hem 4096 colors, which is also in a tricky way. By tricky, I mean the 32 colors of half bright are halved in terms of color. So if you were using, let's say, a value of 8 as red, it will become a value of 4 in the second set of colors. Okay, so if number in color index 1 was value of 8, had a value index of 8, color index number 32 would have a value of 4. So you don't really have control. You cannot really change the color of number 32. You only can change the color of number 2. sorry, 1 basically. Okay. High res, as I said, maximum colors is 16, and there are no special modes for high res. That's what it is. 640 by 256, and that's the maximum. You can have interlace, of course, which he will talk about it, but in terms of colors, it's always 16. So the modes that I mentioned have, you know, half bright, and hem have more colors. Hem provides 4096 colors. Okay. So here he is going to say what I just repeated before, that 2-bit planes, 1-bit plane is 2 colors, 2-bit planes is let's see if my notes will display there. Yeah, 2-bit plane is 4 colors, 3-bit plane is 8 colors, 4-bit plane is 16 colors, 5-bit plane is 32 colors. I already explained that. So here he's giving an example of how the bit planes are combined, and because you have 3-bit planes, then you end up with 8 colors. Okay, so if the colors are all 0, then that is color index 0. Okay, so this is bit plane 1, bit plane 2, bit plane 3, and this is how they are combined on top of each other. And each bit, okay, each bit, if you had to look from top of it, what's on top and under it and under it, those 3 form the color. Here he gives another example using 4 bit planes and the combination of all bits together. So you have 16 combinations. The same thing happens when you have 5-bit planes. So here we have 4. If you have 5, it's the same thing. So again, him gives importance, and this is what I was saying, but now he shows it in a diagram. He shows it as you know, 2 colors. 1-bit plane is 2 colors. 0-bit planes, of course, there are no colors except the background color, which is 1, which is DFF 180. 2-bit planes is 4 colors. So I've said this many times, and so now you have an image which you can connect to, and I think the image makes sense. Also, now he explains that there are 32 colors, and that means that there are 32 registers. Okay, the first register is, as you all know, is DFF 180. Okay, and we have from DFF 180 till DFF 1BE, which is not written here, but you should be able to see on my notes. You should be able to see it. Index 31, DFF 1BE. Okay. So if we have a 4-bit plane, that is 16 colors. If all the bits aligned on top of each other are at 0, then we have color index 0. This is an explanation now of what I showed you in my own diagram, okay? Which hopefully you understood, instead of, you know, seeing it in words here. I think it makes more sense. At the same time, if we have 5-bit planes and that is 32 colors, all the bits set, then we have color index 31. Of course, all the bits set, okay, all the bits 1 of the 5-bit planes is 32. In AGA, okay, remember the A1200 and the A4000 has got the AGA chipset. They have 8-bit planes, not 6-bit planes like the Amiga. The 6-bit plane is used for what we discussed before, to have either half bright or hem, okay, the 4096 mode, but normally use bit planes 1 to 5. In fact, in AGA mode we have 6-bit planes which produces 64 colors, 7-bit planes which produces I'm going to leave my notes there, which produces 128 colors, and 8-bit planes, which produces 256 colors. All bit planes together form what is called a playfield. Okay, so if we have 3-bit planes together, that's a playfield. Now, this formula is quite important, and I already explained it in a way, but now you see it written. How you calculate the size, okay, of how much a screen will occupy. So the first one is bytes per line. Okay, so we have 40. If we have 320, so it's 40 by lines per playfield, which is that if we have 256, then times 256, then the number of bit planes. So if we have 5 is 5, so 40 times 256 times 5, if we were talking about a 5-bit plane low res screen. Let's now analyze, okay, the register BPL con 0. Okay, so of course the register is when we tell the Amiga what resolution we want and how we want it and what modes we're going to use. Remember, at 0 means a bit is off, and the 1 means a bit is on. This diagram is the values that we put in BPL con 0, DFF 100. Okay, I mean this register you use a lot. You will learn it by heart, BPL con 0, because it's something that you always need to set up. Let's put it this way. Okay. So bit 15, okay, if it's at 0 means low res. If it's a 1, it means high res. Okay, now bits 12 to 14, okay, are what we use to define our bit planes. So if bit 12 is 1 and the others are 0, we just have one bit plane. Okay, if bit 13 is a 1 but 12 is at 0 and 14 is at 0, then we have 2-bit planes. So it's binary, from 0, which means no bit planes, 1 is the first bit plane, to 7. But remember, we only have 6 in OCS chipset, so we can only use from 0 to 6. Then we can specify with bit 11 whether we have ham, hold and modify on or off, the 4096 modes for low res. Of course, we cannot have it for high res. And then the Amiga has another mode which I haven't mentioned yet, which is dual playfield. So dual playfield, or double playfield as we call it here, is a mode where you use the odd bit planes and the even bit planes. So you have, let's say, 4 bit planes. You have bit plane 1, bit plane 2, bit plane 3, bit plane 4. Bit plane 2 and 4, okay, they are even number. Okay, so those are the even bit planes. And then you have bit plane 1 and bit plane 3. Those are the odd bit planes. So you can draw an image using bit plane 1 and bit plane 3 and have it superimposed over the other image, okay, of the even image, or vice versa. So you decide how there's another register that decides the bit plane priority. This is how Shadow of the Beast creates that effect, okay, of having something further away and something closer, and that's how it manages to have more colors. That effect of parallax. Basically, you can only have 2, but by hardware, using the hardware, you can only have 2. Using software, that's a different story. Then we have a bit that should always be on, which is bit 9. If you remember from the previous chapter, the default value for DFF 100 was 0200. Okay, that 2 is bit 9, and we need to have it on to be compatible with the Amiga 1000. Then this one we can ignore, it should be at 0. These bits 7, 6, 5 and 4 should be at 0. Okay, they are not used on OCS chipset always. Bit 3 is for light pen, so we don't use, so it should be at 0. Bit 2 we might use, it's interlace, okay, when we double the scan line. So if we had 256, we double them and we get 512, okay. And then bit 0 should be at 0, and bit 1 should be at 0, and bit 0 should be at 0 too. So what you really need to consider is from bit 8, okay, to bit 15, okay, the high part of the BPL con 0. And then you need to remember that there is bit 2 that indicates whether we are using interlace or not. Start accepting, okay. In this chapter he is not going to explain certain things. There are certain registers which we're going to fill them up with default values, okay, and for now just accept them. In the next chapter he will be explaining these values and why they are like that, but for now accept that to have a basic screen, fixed screen and nothing else, you need to set up these registers as he will be recommending. So for example, one of the registers is DFF start and stop, which is register 03, 03C and 0038. Sorry, which is register the 4 and the 0, and we fill them up with 3C and 38. Okay, I see. Yeah, because because I might not read the messages, so I had to say that just in case you asked and I missed it. But yeah. So bits 12 to 14, as you saw here. Actually, here he's going to repeat, so we can, I already explained it, I already said what these bits mean, so we can skip these. The notes are what I just said. Yeah, I'm just making sure that I am not, you see he's saying leave them as 0, and here this bit which is bit 2, which is, it gives you 512 lines, so we can skip to here. This is these are examples, okay, of default values for the screen. How to say, I mean, there are more combinations than this, but he is kind enough to show us that these are values that we can put in register 100, okay, the FF 100, with these values. So here he's specifying 4-bit plain low res, okay. Here he's specifying 3-bit plain high res plus interlace. Here he's specifying 6-bit plain half bright. Here he's specifying 6-bit plain, okay, ham low res. Here he's specifying dual playfield. Remember what I said about dual playfield, and he's using all 6-bit planes, so 3 odd and 3 even, or 3 even 3 odd plane in low res. Here he's using 2-bit planes, sorry, dual playfield again, 2-bit planes odd, 2-bit planes even, and he's using high res interlace. It's just some examples. There are a lot more, because you can combine all those modes. So we were used to see it empty, okay, just 0 to 100, 0, or in this format. So the 200 here is this. So remember, bit 9 needs to be set, as I said, because of compatibility issues with the Amiga 1000. So that is why it is there. Here he's giving BitCon 0 bit 12 on. So if we do bit 12, we have 1 bit plane. Okay. If I refer back to this, remember these 3 bits define the bit plane. If we just enable bit 12, is the first bit plane, so we only have 1 bit plane. So we did this. He continues here now to show 2-bit planes, 3-bit planes, 4-bit planes, 5-bit planes, 6-bit planes, and each time he's changing these values here. Okay. Here he was specifying half bright also, so he enabled bits 14 and 12, and those gives us half bright. Ham here he's using actually half bright. Yeah, this one was ham, this is half bright, and this is the 6-bit planes basically. So here is what I said. He's going to talk about the registers that you need to accept the values in them for now. This is the first 2 registers. DDF start and DDF stop means data fetch start and data fetch stop, and we populate them with 3C and D4 for low res. Okay, in high res, I think he mentioned it. Maybe no. Yeah, in high res, no, he didn't mention it. There will be a different value basically. Okay, so with it, I explained that the data fetch start and stop should be 3C and 9.4 and D4, sorry. Remember, if you have Intel lace, you need to enable bit 2 to jump to 5129 instead of 256. Once you have done all the above settings, once you have done all the settings and also added this register, you need to set the bit plane pointers. Okay, each bit plane has got a pointer. The screen is made up of, as you saw, an image is made up of bit planes. Each bit plane on top of each other gives us the color. Okay, so when we know where the start address is of the bit plane of the image, if we add the size of 1 bit plane, we know where the second bit plane starts, or the bit plane 1 where it starts, because the first one is 0. And we populate these registers for each bit plane. As I said, there are 6-bit planes, but normally 5 are used. He is going to tell you, he's showing here how to set up the bit plane pointers. Okay, so E0 has got also E2, which is remember these are 16-bit registers, but E0 and E2 together are 32 bits. So when we move dot long at E0, we are actually moving along word which populates E0 and E2. although we can do the above, remember that this needs to be written every frame. So here is just for you to understand how it is done with the CPU. But in theory, you don't do this. The reason why is you have to update it every frame, and the best person to update every frame is the copper, not a program that you wrote. We need to set the copper list with these special registers. So here he's going to talk about more registers that we need to set up. So he covered data fetch start and data fetch stop. He covered these two, but actually there are also these. Sorry. Yes, those two he defined, 92 and 94. So we already covered these two. Come on. But we need to cover with the others. Okay, the others also needs to be initialized. So the first one, okay, data fetch, data display window start, sorry, and display window stop, okay, is where our screen is located on the monitor. Let's say that way, where it starts and where it ends, and the values are 2C81 and 2CCC1, 2CC1, which means that we have a 256. You know, the difference between 2C and 2C is 256. If you start from line 2C at the top and starts going down, once we reach FF, and this is a PAL screen, then you go to 2C again, so that makes it 256 or 256 lines. The others, bit plane and modulo, are 0. Okay, so these registers needs to all be initialized. After that, so we initialize the registers. Okay, so here is a simple copy list. Now we are coming to defining a copy list to display a screen. So this screen is made up, we define it using this list. So these lines here is what's up here. So all we need to do once we define this is tell BPL con, hey, we need this amount of bit planes, and we put that value here. Okay, so we initialized these values, and then we tell it how many bit planes we have. Here, remember, an image needs colors. Here we are defining the 32 colors for the image. These are the color registers for 32 colors. And of course, we're telling the copper, this is the end of our copper list. So this copper list, what you see here, is enough. You don't need more. In theory, I'm just going to make an exception in a minute. But if we were using just OCS machine, is enough to display a screen. Okay. We need to hold on, I think we are in page 49. We're going to start page 49, and somewhere I need to see where. There you go. So that's when we cover the example. Okay, so that's where we are. So somehow, okay, we need to tell the assembler where our image is, and it needs to load it. So there's a command in the assembler called ENG bin. Okay, and this loads an image, a raw image, always raw. Okay, a raw image, and attaches that image to our assembly file. Okay, and like that we can point to it, to the image, and we can get to know where the bit plane pointer, the first bit plane pointer is for our image, because we linked it to our file, we load it into our code, and we put a label there which tells us the image on the screen. So ink bin, I'm just going to jump a bit on the example. I mean, we should cover the example a bit later, but to see what I mean. So here is how we load the image. Okay, this line, we are loading the image. Okay, so we loaded an image in our file, and then we put a label to it. So now we know that if we point, if we do move long immediate hash pick, we know that that is the address. We will get the address of where our image is and the first bit plane for it. And that's how we can calculate and load and calculate the bit planes and load an image, basically. Anyway, we will come later to that, but because he mentioned include bin, I thought I'd show it to you in the assembler. So here is one of the, unfortunately, okay, this is a mistake by Fabio of having an image, okay, that is named, okay, Amiga.320 star 256 star 3. Why? I'm saying it's an issue. The Amiga accepts in a file name to have star, but when you transfer a file to PC or to something, not on the Amiga, the star is ignored and probably the file is not loaded. So when you go onto the disks, when you download the disks of Fabio, okay, Randy of RamJam, you will not find this file. Okay, this chapter uses this file called amiga.320 by 256 by 3. So I had to create my own image. So now here is the nice part of me. Okay, I'm going to give you some homework. Because there is no image on the disk, okay, please create an image 320 by 256 by 3, okay, and it has to have some background which is black, basically colored 0, so that we can display things behind it. But yeah, that is my homework, and I am, or assignment as we call it in the modern world now, not homework anymore. I'm giving you an assignment of using either Kefren's or the AGA IFF converter, or Ozzy in his case his own his own converter, and basically create an image. There are other instances where the images are not on the disks, and it's because of this. When they transfer them, the images were lost or were not transferred, because neither Linux nor Windows like asterisk in a file name. So that caused the problem, and you will see as we proceed that we will encounter more issues in relation to this. However, it's not an obstacle. We will go around them as you see. So this is to make you aware about issues of the disks. When you go and execute a file that there is from the book, it might not assemble because it tells you I cannot find this file, and this file is because they used file names, Fabio used file names with a star in them. Now, just to make you aware, if you had to copy, if the files were on disk, okay, and you had to copy them, if somebody, you know, has still the disks of the Amiga, the original disks of Randy, and transferred them in WinUAE, WinUAE is intelligent enough to replace the star, the asterisk, with an underscore. However, the file will still not load because you need to go and rename the file with an asterisk and put an underscore instead. But just wanted to make you aware that WinUAE is intelligent and knows about the star issue, and it will convert an asterisk into a star or a double underscore. It depends about on the name of the file. I did test WinUAE for the star, and it does convert a file into a star, into an underscore from a star. So quite intelligent. I was quite surprised to see WinUAE doing this, but unfortunately the disks were not transferred during the time of WinUAE probably, so that was lost. But if anyone has got still the disks, the original disks of Randy, then you should have the original file. And I would love to get the original images actually. So if anyone manages to get the original disks and converts them to ADF, it would be great, because the ones on the website or in Aminet do not have it, do not have the original file, do not have some files because of the asterisks in their file name. It's good idea, okay, and this is, I advise you to follow Randy's pattern except for the asterisk, but use an X instead, or an underscore to name the file name of an image, the name of the image underscore, and then the resolution of the image and the number of bit planes. And also use a system like .raw 0, .raw 1, where one will be without colors, the other one will be with colors, so that you know what type of image that is. Because an IFF image, you don't need those specs because it's able to load and display the image irrelevant of the format. But a raw image, you need to know these parameters. So it's a good idea to write the number of bit planes, and if it's ham or half bright, also make a note in the file name. So the file name becomes a bit long, but it helps. The Amiga supports it anyway, unless you're using Kickstart 1.2. I think Kickstart 1.2 was limited to 64 characters, but not Kickstart 1.3 and afterwards, or maybe from Kickstart 2.0. The length, the file name length was increased. I can't remember, but maybe Ozzy can tell me. I'm making sure you don't sleep, Ozzy, so I just ask you a question. Maybe you know. So we will need to add the populate the bitplane pointers with our addresses for the image. We did this, no? I covered the move. We are using move, we're using the bitplane pointer to id0 and d4. So here we are covering 2 bit planes. Here we are covering 2 bit planes again, but notice we are using, remember, an address, the custom chip registers are 16-bit, and so we split the address in 16-bit numbers, and we are populating id0 with a number with the high word of the first bit plane, and then id2 with the low word of the bit plane. And Same thing for bit plane 1 and bit plane 2. So he is now, let's say, extracting or making it better, okay, by showing. So here he used the CPU, and here he's showing in the couple list. Okay, so the source we are having the registers of the couple list here. So one bit plane is using registered E0 and E2. Remember, it's 16-bit, but together they make 32-bit. And we store the high pointer and low pointer of the bit plane in this register and in the same register. If we had two bit planes with these values, so bit plane 1 contain 23400 and bit plane 0, and bit plane 1 contains 25C00, then the high word of bit plane 0, which is E2 E0, will contain just a 2, okay, but the low word, which is E2, the address of the register is E2, it will contain 3400. So the same thing will be for bit plane 1. So this was bit plane 0 and this is bit plane 1. I mean, guys, even if you do not understand it area, this is, I mean, logical looking at the code, and this is why I started highlighting the code to make it obvious, because I will explain this, but this is what you need to understand, and he's showing it. So don't be discouraged because the text on the screen is in Italian. Now, the 68000 has got an instruction called swap, and we're going to cover it. So basically, if you move a register, something into a register, it always works on data registers, okay? In this case, we're moving something into D0, okay? Then, if we do swap, what happens is the high word, remember an address is always long. Then the high word becomes the low word, and the low word becomes the high word. And this is how we swap, and we can exchange and do this in our code. And this is a typical example, typical routine, okay? Very simple routine that we use to update the bit plane pointers on the Amiga in the couple list. So what we have here, remember, we have the bit plane pointers here, and we're going to update them with a value, okay? And these are initialized at 0. So this is bit plane 1, bit plane 2, bit plane 3. So we are going to populate each bit plane. Now we loaded our image, okay, called pick. I mean, even the code that I show you in as in 1, okay, as hash pick in the 0, okay? So the address of our image is in the 0, and the first, even if the image starts where the 0 says, but that means also the bit plane 1 starts where the image is. So the 0 will hold the start of our first bit plane image. Then we are saying where the bit plane pointers are. So A1 will point to the bit plane pointers, and we have A1 pointing to this in line number 2 where E0 is. Okay, actually we are pointing before the E0, and I'm going to show you here because he shows it here. Here we don't have a 0, 0 in front of it 0, but here we have it. Remember, these are word aligned. They are always word aligned. So there's a 0, and in fact that's why we use this define constant.word. We are pointing A1 where our bit plane pointers are, and we're saying we have 3 bit planes. Why number 2 and not 3 here? The reason why is we count the 0. So from 0 to 2 is 3 times, no? And this is going to be the loop. So D1 is going to be used as the loop counter, like a for next loop, basically, to update the bit plane pointers because we have 3. Now, this is where things might sound complicated, but or seem complicated, but they are not. Why? So the first 0, so we have 6 A1. So we said that A1 points to here, the beginning, okay, in line 2. And remember, there's a 0, 0 in front of it's 0, and he's showing it here, okay? So the first one is E6, is 6, comma A1. So 6, comma A1 is here, okay? So we populate the image, okay, with this value. If it was 2, 3, 4, 0, 0. Now, what happens is we do a swap. So what was high becomes low, and what was low becomes high in the data register. So then we move it, but this time to 2A1. So we move it to here, and that becomes the value 2. Then we put the 0 to the same as it was. So we swap again high with low and low with high, so that we get the same answer when we load it first with the image. Okay, we get the same value. Then we add the size of a bit plane, which is 40 times 256, to the 0. Okay, so now we got the address of the second bit plane, or bit plane 1, because this was bit plane 0. And then we add 8 to A1. So bit plane, we first pointed this to here, okay? Now we are telling it to point to here, okay? Where there is, in line 3, where there is the first 0. And then we loop, okay? We decrement the 1. That's basically it. That's our standard routine of how to update the bit plane pointers. Here, okay, he is explaining what we just said. So first we pointed to the first byte here, okay, and then we pointed by adding 8, okay, when we do add word add quick.w, okay, immediate 8, 1, we're adding 8, we come to this, we come here, basically we make it point to the first 0, 0 in line number 4, okay, and we continue doing that. And like that we have our routine that displays the bit planes. Remember, decrement and branch means it decrements the register, which is the 1, and loops back to here, okay, where we tell it. So it's looping till up here. It's a for next loop, basically, in assembly, something that the which the 6502 had. So we arrived, okay, at lesson the first example for A. So let's see what lesson 4a is showing us. I'm going to finish also with this lesson. Okay, so we have our source here. Now, just to make you aware, Fabio wants us to learn how this routine works. So the initialization bit where we kill the system and then we restart the system is not here. He wants us to debug this and execute the code step by step and see what happens so that we can understand better what the swap command does. Okay, and also how we are populating the bitplane pointers. If I do, so remember we are loading the image using the ink bin, okay, and we are loading this image. Remember, this image is an image that I created, okay, because on the disks it's not there. It has also color at the end of it, okay, row 1, not row 0, and we are pointing to it using pick. So if I assemble it and I execute it, nothing is going to happen. As I said, it doesn't have the part that display what we need, but we need to just debug it so that we understand what it's doing. So AD, okay, in the assembler, I get the debugging window for you guys to see. Okay, now start noticing the values here when I start executing one by one each instruction. Okay, so the first one is we're loading the address where our image is in when the address of the image. So we executed the first line, and you can see that we got 401b 3584 in the 0. So that is the image, the address of the first bit plane, basically, or the image. Then we load the A1. Okay, so A1, which has got something here right now, but we're going to update it with the bit plane pointers. So if we do that, we see that we have this value in A1. Okay, then we're going to, sorry guys, I made a mistake, I pressed the wrong key. Let's start again. So that we loaded 80, that we did, that's the address. We have a different address now, of course, because remember the Amiga is dynamic in terms of addresses. Then we load the bitplane pointer, which is in A1, so pointing here. Okay, then we're going to populate D1 with a 2. Then look what's going to happen. We do move.quick, okay, sorry, move.word, okay, did 0 into 6 bracket A1, so offset of A1. So what do you think the value of that we're going to move into A1 is going to be? Of course, it's going to be the 3584 because we said word, so we're going to take the low word of that address, and we should see that value in 3584, which for now I will continue to execute the program, then I will show it to you. Then look what's going to happen to the 0 when we do swap the 0. So remember, we have 401b 3584. Okay, look what the instruction does. It inverted it, so we got 3584. So what was low byte became high byte, high word, and what was high word became low word. So now we can move the 401b into the offset of 2A1, and then we need to put it back to what it was. Now the actual address is 401b 3584. And there you go. That's what it does. Now we're going to add the size of a bit plane. Remember, we have a 320 by 256. 320 is 40 bytes. 40 times 256. We add that to the 0. So the 0 is going to be incremented by 10k, basically, because that's the size of one screen, of one bit plane. Now, A1, which points to our bit plane pointers, is going to be incremented by 8 so that we update the next pointer. And as you see, that was incremented by 8. Now the 0, the 1, is going to be decremented and we jump back to the loop. So that should become a 1. And we continue doing this, okay, till we populate all the bit plane pointers. Now, remember, our bit plane pointers are defined here. Let me show them to you. Are defined there. So if we do m, okay, let's see how we populated them. If we do m ppl pointers, we see that we should have 0 E0, so E0 the next address. Remember, there's always a 0 0 in front of that. And then we should see our address, which was 4 or something, I cannot remember, which was the high word for 0, and then 1B. So that was, remember, they are 16-bit. So that was the high word for first bit plane. Then the second bit plane, okay, which is E2, so that's 0 0. Remember, it has a 0 0 in front of it. E2, we get the low word of the first bit plane, which is 3584. Now we get the address of bit plane 1, because this was bit plane 0. So 0 0 E4, okay, and then we get 401B, and then 0 0 E6, because that's this, and then we have the 5D84. So if you had to do, so bit plane 1 is at 401B, 5D84. If you had to subtract this 401B, 5D84 from 401B 3584, you should see a difference of 10k, which is one bit plane, the bit plane size. Remember, they are in hex. Actually, we can do that. So print the address is 401B 5D84 minus 401B 3584. I think I need to put hex in front, because these are hex numbers. And there you go, 10k, 10240. So we did lesson 4a. Okay, so thank you very much and see you next week.